Everyone says black holes are born from dead stars. This one was never a star at all. Right now, deep in the early universe, a black hole the size of an entire star cluster appears to have just turned on, fully grown, as if someone flipped a switch. And if you want to be the first to hear stories like this one, raw science with no hype, hit subscribe now and stick around because the next few minutes will change how you picture the first chapter of the cosmos. Long before telescopes, humans looked up and wondered how everything began. They told stories about gods and giants and great floods of light. Then, less than 100 years ago, scientists figured out that the universe is not just old, it is unbelievably old, almost 14 billion years old, and that at the very beginning it was tiny and hot and dense. In that first tiny moment, every bit of matter and every bit of energy we see today was squeezed into a space smaller than a single atom. Then space itself stretched out fast, faster than light, in a flash we now call the Big Bang. That moment happened about 13.8 billion years ago, and it left behind a sea of gas, mostly hydrogen, spread across a dark and empty new universe. For the next few 100 million years, that gas did almost nothing. There were no stars, no planets, no galaxies, just cold darkness drifting outward. Slowly, in some places, gravity pulled small clumps of gas together, and the very first stars lit up. Those first stars were strange and huge, much bigger than our sun, and they burned out fast. When they died, some of them collapsed into black holes, which are points in space where gravity is so strong that even light cannot escape. For decades, scientists believed this was the only way a black hole could form. A star dies, the core collapses, and a black hole is left behind. That belief became the standard picture. But here's the problem with that picture. Black holes made from dead stars are small at first, maybe 5 times the mass of our sun, or maybe 100 times the mass of our sun if the star was large. To grow into the giant black holes we see today, sitting at the center of almost every big galaxy, they would need billions of years of slow feeding. Yet the James Webb Space Telescope keeps finding huge black holes way too early, way too big, and way too soon after the Big Bang. Something about the old story did not add up. That gap between what we expected and what we see as the mystery this new discovery finally cracks. In late 2023, 2 powerful space telescopes, the Chandra X-ray Observatory and the James Webb Space Telescope, both aimed at the same small patch of sky, they were looking behind a giant galaxy cluster called Abell 2744, also nicknamed Pandora's cluster, about 3.5 billion light years from Earth. The mass of that cluster bends space around it like a giant magnifying glass made of gravity. Behind it, hidden by distance, was a tiny faint dot of light that most telescopes could never see. That dot was a galaxy, and scientists named it UHZ1. The number comes from the survey that found it. The ultra-deep field follow-up with Chandra, called ULX for short, plus H for Hubble, and Z for redshift. Redshift is the way scientists measure how far away a thing is by how stretched its light looks. When the team checked UHZ1 with Webb, they found that its light had been traveling toward us for 13.2 billion years. That means we are seeing UHZ1 as it was only about 470 million years after the Big Bang. Think about that for a second. The universe itself was younger than our Earth is today when the light we are now seeing left that galaxy. Compare this to looking at an old photograph of someone as a baby. We are not seeing UHZ1 as it is now. We are seeing it as it was almost at the very beginning of cosmic time. The Chandra telescope, which sees X-rays instead of regular light, picked up a strong X-ray signal coming from the center of UHZ1. And that signal is the fingerprint of hot gas swirling around a black hole. The gas is so hot, millions of degrees, that it shines in X-rays the way a hot stove element glows red. From that fingerprint, the team, led by astronomer Priyambada Natarajan at Yale University and a group including a researcher named Akamatsu, was able to estimate the mass of the black hole inside UHZ1. The result was shocking. The black hole was not 5 times the mass of our sun. It was not 100 times the mass of our sun. It was somewhere around 10 million times the mass of our sun, possibly up to 100 million times the mass of our sun, all packed into a single point at the center of a tiny baby galaxy. Now here is where the real mystery begins. The mass of the black hole and the mass of the stars in UHZ1 were almost equal. In modern galaxies like our Milky Way, the black hole at the center is usually 1,000th of 1% the mass of all the stars around it, a tiny speck compared to the whole galaxy. In UHZ1, the black hole was huge compared to its host, like a toddler carrying a bowling ball. Scientists call this an overmassive black hole. It means that the black hole did not have time to grow slowly from a seed. It had to be born big, almost instantly, skipping the slow buildup phase that the old theory relied on. So how do you make a black hole that size without using a star? The leading explanation, and the one the UHZ1 data points to, is called direct collapse. In this picture, a giant cloud of hydrogen gas, perhaps tens of millions of times the mass of our sun, never forms stars at all. Instead, something keeps it from breaking into pieces. Maybe the radiation from a nearby young galaxy kept the gas too hot to collapse into stars. Maybe a shock wave from a young supernova pushed the gas together just right. Whatever the reason, the gas cloud keeps growing and growing, hanging together as one massive blob until finally it cannot hold itself up. The whole cloud collapses inward at once like a giant puddle falling down a drain, and a single huge black hole is born. No star phase, no slow growth, just one massive birth event that turns a cloud of pure gas into a giant, silent, hungry point in space. The UHZ1 black hole fits that picture better than any black hole we have ever seen. Its mass matches the mass of the available gas in its host galaxy. That is exactly what direct collapse would predict. The paper describing this was published in the journal Nature Astronomy on November 6, 2023, and it became one of the most talked about astronomy findings in years. Many scientists had predicted direct collapse black holes for decades. Until UHZ1, we had never seen a clean example that matched the theory so well. This was not just another pretty galaxy picture, this was a piece of evidence that part of the old story, the part about slow growth only, was missing a whole chapter. To appreciate how big a deal this is, imagine you are a detective and you find a fingerprint at a crime scene from a person nobody has ever met. That is what UHZ1 is for black hole science. We had theories about how direct collapse could happen, but we had never caught one in the act. Now we have a real object that fits the theory like a glove, and it is not just one example. Other Webb discoveries in 2024 and 2025 have shown more and more baby galaxies hosting huge black holes in the first few 100 million years of cosmic time. The pattern is becoming hard to ignore. Here's where the story gets even stranger. If direct collapse really happened often in the early universe, then the very first big black holes did not need billions of years to grow into monsters. They were born as monsters. And that means many of the giant black holes we see today sitting quietly at the centers of old galaxies may have started their lives as giant newborn black holes in the first half-billion years after the Big Bang. Our own Milky Way has a giant black hole at its center, about 4 million times the mass of our sun, called Sagittarius, a star. If direct collapse is real, that monster may have begun as a direct collapse seed too. Over time, it grew by eating gas and merging with other black holes, but its earliest seed could have been huge from day one. This also changes how we think about the very first galaxies. In the old picture, galaxies came first and black holes came later, gradually building up inside them. In the new picture, sometimes the black hole came first and the galaxy grew around it, like a city building up around a central monument. The UHZ1 finding hints that black holes and galaxies grew together from the start, shaping each other from the very beginning. That is a big shift in cosmic history. It means black holes are not just passengers riding inside galaxies, they are pilots helping to steer the way galaxies form. Let us slow down and look at exactly why this finding is so strong. 3 reasons stand out, and each one matters in its own way. First, the distance is real and confirmed. UHZ1 sits at a redshift of about 10, meaning the light left it when the universe was only 470 million years old. That number is not a guess. Multiple instruments, including Webb's near-infrared camera and spectra, all agree. Second, the X-ray brightness is real and confirmed. Chandra's deep field observation caught a clear X-ray point source that matches the position of the galaxy. X-rays at that brightness cannot come from normal stars. They are the smoking gun of hot gas falling into a black hole. Third, the ratio of black hole mass to host galaxy mass is real and confirmed in UHZ1. The black hole is roughly the same mass as every star in the galaxy combined. That ratio is the signature of direct collapse because only a single massive birth event can produce such a match between black hole and galaxy mass so early in cosmic history. This pattern of expected versus actual versus Y matters here, and it is worth repeating for the next big finding. Scientists expected direct collapse black holes, if they existed, to look like overmassive black holes in very young galaxies. What they actually found in UHZ1 is exactly that. The black hole is overmassive compared to its galaxy stars, and the galaxy is extremely young. Why does this matter? Because until now, every single black hole we had seen in the early universe could be explained away by saying it must have grown faster than we thought or had a head start. UHZ1 cannot be explained that way. The mass is too large, the age too young, the evidence too clean. Something other than slow growth had to happen. Here is something worth pausing on. If you had to guess, do you think the black hole in our own Milky Way started out this way, born huge right at the edge of cosmic time, or did it grow slowly from a small star death? Drop your guess in the comments right now. And if you are enjoying the way this story is unfolding, hit like so more curious people find their way here, and subscribe if you want raw space stories without the hype. Now let us zoom out and feel the scale of what we are talking about. Our sun is 1,300,000 times the size of Earth. That is already hard to picture. A black hole 10 million times the mass of our sun would have a sphere of influence roughly the size of our entire solar system, and it would warp space so deeply that light from stars behind it would bend in a circle around it. If you stood close enough to see it, you would not see the black hole itself. You would see the whole sky wrapped into a glowing ring, an effect called gravitational lensing, the same effect that helped us find UHZ1 in the first place. Now imagine that object surrounded by a baby galaxy full of brand new stars, only 470 million years after the universe began. That is UHZ1, and that is what Webb and Chandra captured. A cosmic newborn the size of a small galaxy sitting quietly at the dawn of everything. What does any of this matter to a person watching this from a living room on Earth? It matters because it changes what we know to be true about how the universe assembled itself. It matters because every black hole we ever find in the night sky, including the one at the center of our own Milky Way, suddenly has a different origin story. It matters because if direct collapse really happened, then somewhere out there in the very early universe, there were probably failed seeds too, gas clouds that almost collapsed directly into a black hole but did not quite make it. Those failed seeds might now look like strange small galaxies with weird chemical fingerprints, the kind Webb is just beginning to spot. It also matters because the next set of telescopes, including ground-based giants like the European Extremely Large Telescope being built in Chile and the Vera Rubin Observatory in the Andes, will be looking at the same era of the universe with sharper eyes. They will find more UHZ1-like objects, or they will find reasons to rethink the theory. We are at the start of a new chapter, not the end of one. The story is still being written, and the next 10 years of astronomy are likely to overturn more old ideas than the last 50. Here's a part of the story that often gets skipped. The Chandra X-ray Observatory, the telescope that caught the X-ray signature of the UHZ1 black hole, was launched in July of 1999 and has now been operating for more than 25 years. That is a long time for a space telescope. Its mirrors and detectors were never designed to spot a black hole 13.2 billion light years away. Yet because UHZ1 sits behind a gravitational lens created by the Pandora's cluster, the X-rays were focused and amplified by the cluster's gravity, just like a cosmic reading glass. Without that natural magnifying glass, Chandra would never have detected this black hole. Without UHZ1 being in just the right spot, the same is true. We got lucky. But in science, luck plus preparation is how discoveries happen. Webb itself only launched in December of 2021, and it took about 6 months to reach its working position about 1 million miles from Earth. By 2023, it had begun seeing the most distant galaxies ever observed, and UHZ1 was one of the very first objects it pointed its deepest mirrors at. The combination of Chandra for X-rays and Webb for infrared light gave scientists two views of the same place at the same time, and that 1-2 punch is what made the direct collapse case so convincing. If either telescope had been missing, the argument would have been weak. Together they draw a clear picture. There is one more important detail. The black hole inside UHZ1 is not actively growing fast. It is what scientists call a low luminosity quasar. That means it is not swallowing huge amounts of gas right now. It is sitting relatively quietly, even though it is massive. That fits the direct collapse model perfectly. A freshly born direct collapse black hole would not need to eat much to be visible. It would already be huge from its birth. A normal black hole that grew by feeding over billions of years would have to be eating a lot to look that big that early. UHZ1 is barely snacking, yet it is gigantic, the perfect fingerprint of a giant seed that was planted fully grown. Now, you might be wondering, if a black hole that big can just pop into existence, what does that mean for how we search for the very first black holes in the universe, the ones that formed before any stars at all? Some scientists think that direct collapse black holes could be the first objects of any kind that lit up after the cosmic dark ages, even before the very first stars. There's a class of objects called little red dots that Webb has been finding in deep images, tiny reddish galaxies that look older than they should. And some researchers now think those might be direct collapse black holes in hiding or direct collapse seeds just starting to grow. The UHZ1 discovery is a kind of proof of concept, a confirmation that this kind of object really can exist. That is huge for future searches. Pause for a second and imagine this. Roughly 13 billion years pass between the moment we are seeing UHZ1 and the moment we are living in right now. 13 billion years. In that time, the universe has expanded massively. Gas clouds have collapsed into countless stars. Stars have built planets. Some planets have built life. Some of that life has built telescopes and pointed them back at that tiny distant moment. We are, in a real sense, looking at our own past. The atoms in our bodies were made inside stars, and those stars had to come after the first generation of stars and black holes that UHZ1 belongs to. Every breath you take, every atom of oxygen, every carbon atom in your hand traces back through this very chain we are talking about. And the discovery of direct collapse is not just a curiosity, it is a piece of our own family tree written in light. To make sure we are not overstating the case, let us look at the doubts and questions that other astronomers raise. Some scientists think that UHZ1's black hole could still be explained by fast growth from a normal stellar black hole seed. If the early universe had very dense gas clouds that fell in fast, that is possible. But the math gets tight. To grow from a 100 solar mass seed to 10 million solar masses in only 470 million years, the black hole would have to eat almost continuously at the maximum possible rate, something that physicists call the Eddington limit. It is not impossible, but it is very unlikely to happen that cleanly that early. The direct collapse scenario is simpler and fits better. Other scientists point out that we have only one UHZ1 so far. One example is not a pattern. That is fair. We need more. That is exactly why the next big Webb and Chandra programs in 2025 and 2026 are hunting the skies for more direct collapse candidates. If they find even a handful, the case becomes solid. If they find many, the direct collapse route becomes the standard explanation for the first supermassive black holes. Either way, the UHZ1 discovery will be remembered as the moment the debate began in earnest. Think about this for a moment. Has the origin story of the universe ever been rewritten twice in the lifetimes of a single generation of humans? In the 1920s, Edwin Hubble showed that the universe was expanding and much larger than people thought. In the late 1990s, two teams studying distant supernovae discovered that the expansion is speeding up, leading to the idea of dark energy. Now, in the 2020s, Webb and Chandra are rewriting the very first chapter, the chapter about black holes. It is a wild time to be alive and a wild time to be curious about space. UHZ1 is not just a point on a graph, it is also a place, a real place in space. Even though we cannot visit it, it is a tiny galaxy made mostly of hydrogen and helium, the two lightest elements made in the Big Bang. And there are almost no heavier elements inside it because the first generation of stars had not yet contaminated the gas with stuff like oxygen, carbon, and iron. That is another fingerprint that supports the direct collapse idea. If UHZ1 were an old galaxy warped by a lens, you would expect to see heavier elements. You do not. The chemistry matches the chemistry of the first moments of cosmic time. Another wrinkle, some scientists had suggested that small black holes could merge many times in the early universe to quickly make a larger one. That is called hierarchical merger. It is not wrong. Black holes do merge. But for that to explain UHZ1, you would need hundreds or thousands of mergers in only a few 100 million years in a tiny galaxy the size of a small star cluster. The math becomes very messy. Direct collapse is much cleaner. It explains the size in one step, not many. Let us also talk about what comes next. The next generation of telescopes will hunt for direct collapse black holes in the first 100 million years of cosmic time, even before UHZ1's era. That is a time when no stars existed yet, when the universe was still mostly dark. If we find black holes there, they must have come from something that was not a star because there were no stars yet. The candidates from that era would push direct collapse from a strong idea to nearly a confirmed fact. The detectors being built right now have the sensitivity for this search. The first results from those surveys will likely arrive in the late 2020s. There is also a quieter question. Could direct collapse black holes exist in our universe today in some rare gas cloud with just the right conditions? The answer is probably no, because the universe is now full of stars, radiation, and heavy elements, and those conditions usually break a giant gas cloud into pieces before it can collapse as one. But in the infant universe, the gas was cleaner and the conditions were just right. That is why UHZ1 looks the way it does. It is a fossil from a special era. Now let us connect it back to you. People often ask why they should care about the distant universe if it is so far away. The honest answer is that everything you see around you, your phone, your coffee, your body, all of it is made of atoms that were forged inside stars that lived and died in galaxies that grew around black holes like UHZ1. Understanding how the very first black holes formed is understanding the root system of the cosmic tree of which we are all branches. Every space mission, every telescope, every chemical element we have ever cataloged begins somewhere in this chain. UHZ1 is far away, but its story is not far from us at all. There is also a kind of humility in this discovery that I want to name out loud. For almost 100 years, scientists believed they had a firm picture of how black holes formed. That picture was not wrong exactly, it was just incomplete. The direct collapse channel was always there in the math, but we had no proof. Now we have proof. And just as often happens in science, the new proof does not throw out the old idea. It sits beside it. Black holes still form from dead stars. That channel still works. But there is now a second channel, a cosmic shortcut, a way for gravity to skip steps and produce a giant directly. The picture got richer, not smaller. And if you imagine the universe as a giant library, every galaxy is a book and every black hole is a chapter heading. Before UHZ1, we had read the chapter introductions but skipped the title pages. With UHZ1, we finally read a title page out loud. It says direct collapse, and underneath it says this is how it really began. Now let us pause and put the finding in plain numbers one more time, because numbers make a story feel real. UHZ1 sits at a redshift of about 10, and that means its light left at about 13.2 billion years ago. The black hole inside it has a mass between about 10 million and 100 million times the mass of our sun. The galaxy around it has a similar mass in stars. The X-ray brightness from Chandra matches a moderate luminosity active galactic nucleus, meaning a black hole that is feeding but not superfeeding. The ratio of black hole mass to galaxy stellar mass is around 1 to 1. In today's galaxies, that ratio is closer to 1 to 1,000 or even less. The direct collapse prediction says the ratio should be close to 1 to 1 in the youngest galaxies. UHZ1 hits that exactly. Every line of evidence points in the same direction. It is also worth noting that scientists tested this with simulations. They ran computer models of early universe gas clouds under different conditions and asked which conditions produced a black hole like UHZ1. The simulations that came closest were direct collapse scenarios in which a massive cloud collapses as one. Other scenarios, like fast growth from stellar seeds, did not match as cleanly. And that is another vote of confidence for direct collapse, coming from a different kind of science, not just observation, but modeling. If you want one sentence to remember, it is this: UHZ1 looks like a black hole that was born full size in a baby galaxy, and that is why scientists are calling it the strongest evidence yet for direct collapse. It is the kind of evidence that does not close a question, but opens a new way of asking questions. Now let us bring in the people who made the discovery happen. The science paper was led by Priyamvada Natarajan, a professor at Yale who has spent her career thinking about how the first black holes formed. Her co-authors included Andy Goulding, an astronomer at Princeton, and a team that included scientists from across the United States, Europe, and Japan, including Akamatsu and his group working on the X-ray data. The fact that so many teams collaborated using 2 flagship observatories with months of careful checking gives the result extra weight. This is not a one-off observation. It is a piece of work that survived intense peer review and was published in a top journal. The Chandra program that found UHZ1 was part of a larger project to study the early universe using gravitational lensing. The team deliberately pointed Chandra at Abell 2744 because they knew the cluster's gravity would magnify anything behind it. They were hunting for X-ray sources from the era of the first galaxies. Most of the time, those searches turn up nothing. This time they turned up UHZ1, and the results stunned them. Most expected to find faint, modest black holes. Instead, they found a giant. Webb's role was to confirm the distance and to study the galaxy's light. Spectra from Webb's near-infrared spectrograph showed the telltale hydrogen emission line shifted deep into the infrared, the signature of a very high redshift galaxy. That confirmed that UHZ1 is not a nearby galaxy pretending to be far. It really is a baby galaxy from the early universe. Together, the 2 telescopes built a complete picture, like 2 puzzle pieces snapping together in space. Without either one, we would only have half the story. With both, we have a discovery that the whole astronomy community is taking seriously. Sometimes in science, the biggest discoveries are not answers, but better questions. UHZ1 is that kind of discovery. It does not tell us everything about the first black holes. It tells us one important thing. The direct collapse channel is real, and that single sentence will shape the next 20 years of black hole science. From simulator runs to new telescope designs to the hunt for the very first black holes in the cosmic dark, let us also step back and think about how much our view of the universe has changed in just 5 years. Before Webb launched, the most distant confirmed black holes were several hundred million years older than UHZ1, meaning they came later in cosmic time. Now we have a black hole almost at the front edge of cosmic history, and it is enormous. In 5 years, our boundary has moved back by hundreds of millions of years, and our understanding has moved back even further. The pace is dizzying. It is also worth noting how much this kind of research depends on patience. The light from UHZ1 has been traveling for 13.2 billion years to reach us. The Chandra telescope had to stare at the same patch of sky for many days to collect enough X-rays to see the signal. The Webb telescope had to take long exposures to pull out the faint infrared glow. The scientists had to test their models again and again. None of this happened in a single weekend. It took years of planning, building, waiting, and checking. Discovery is often slow. What does that mean for the next chapter? We have every reason to expect more UHZ1-like objects in the years ahead. Each new one will sharpen the picture. By the end of this decade, scientists may have a catalog of direct collapse candidates that turns this into a textbook finding. Some of those candidates may be in galaxies we already have data for but did not recognize yet. New analysis of old Webb images may already be hiding future UHZ1 finds. There is also a poetic side to this finding worth saying out loud. Imagine a black hole being born not from the death of a star, but from the wild ambition of a giant gas cloud. It is a kind of cosmic shortcut, a way for nature to skip the slow steps in a universe full of slow building where stars take millions of years to grow and galaxies take billions of years to mature. Here is one event where everything happens in a cosmic blink. That feels rare and special. It feels worth telling someone about. Now think about your own moment right now. You are sitting somewhere watching this video, and somewhere far away, light that left UHZ1 billions of years ago is just arriving at our telescopes and being turned into pixels on a screen. The story is literally reaching you. You are the latest step in a long chain that started with a gas cloud collapsing somewhere in the dark. Does that make you feel small, or does it make you feel connected? There is no right answer. Both are true. If you have stayed with the story this far, you have earned the final reveal. Here it is. The direct collapse channel for black hole formation is not just a theory anymore. It is an observed phenomenon. UHZ1 is the first clean example, and it changes the way we will write textbooks from now on. The slowest channel of black hole growth is no longer the only channel. There is also a fast channel, and the fast channel may have built the very first giants that seeded the universe we live in. So what should you do next? Subscribe to this channel if you want more deep space stories like this, stories told without hype, without fluff, just the real science and the real people behind it. Turn on the notification bell so you catch the next one as soon as it drops. Drop a comment telling me, do you think direct collapse was common in the early universe, or was it a rare event, and why? And send this video to one friend who loves space. They will thank you, and you will have made the universe a tiny bit bigger for someone you care about. Thanks for watching. Stay curious, and I will see you in the next one.